question, and some of you know me. Many of you are probably too young, so you may not know me. So I'm in Swansea still, and this is not just work by myself. So this is collaborations with other people, and I just put up some of the people who've contributed up on screen. He is currently doing a PhD at USC, but he's a major in the army and he wants to become an academy professor. So he's absolutely brilliant. He produces like the work of 10 PhD students. He's extremely smart and extremely organized. If I could be like that, then I would be so happy. But unfortunately, anyway, so let me start with an overview of the talk. What is robust control and why does it even matter? Basically, then, so I want to start with that, and then I'll start with a bit of a review of classical robust control, because I realize this is an audience, the control is on the program, but it's a different area of control. And sometimes it's a bit like you have an elephant, right? And say, maybe you examine the trunk and I examine the ear, right? And you really need to look at the field from different perspectives and bring it together. So what I will talk about might be a bit orthogonal. So I'll give a bit of an overview of classical robust control techniques, because I sense based on the talk so far that people may not be familiar with that. Then I will talk about why we need different tools for quantum systems and some measures for quantifying robustness for quantum systems we've looked at. We've done a little bit of work using structured singular values, log sensitivity, and our robustness infidelity measure. And then I'll hopefully have some conclusions if I'm not out of time before I get there. So what is robust control? So robust control is about designing systems that are able to function properly in the presence of uncertainty and variations in the system or environment. And the uncertainties can arise from many different sources in any kind of classical system, as well as in a quantum system, measurement noise, parameter variations. So even if you design an aircraft, there will be tolerances on all of the components. And there could be random external disturbances, you know, like a gust of wind or something. And robust control is absolutely critical if you want to take physics experiments out of the laboratory and turn it into technology. So there has been an awful lot of talk about technology, but most of the time we're still talking about physics experiments, and it's not clear if there's a translation. And I think robust control is what you would need. If you cannot make your physics experiment into something you can put in a box and it will work in the presence of all of these disturbances, you're not going to have technology. So let's say the difference between technology and a physics experiment. I could do an ESR experiment in a physics lab. You know, that's a physics experiment. An MRI scanner, that's technology, because some medical technician can operate this machine and it does a lot of complicated things, manipulating quantum degrees of freedom, but you have to have no understanding basically of quantum mechanics, RF coil design, pulse sequences, or whatever. So that's the difference between technology. So classical robust control, the goal, unfortunately, is it possible for me to actually use this kind of, how does this?
Can you remove, you should first remove the USB key at the bottom.
No, it's okay. There's a laser pointer. You just activated it.
And how do I,
Now you're holding it the wrong way around. You're pointing to yourself. Yeah. At the very top.
move,
You want to move forward?
move forward on the laser pointer?
Okay, well then you have to follow Robin's instruction. So
Maybe it would be useful otherwise. I mean, if it's too much trouble, then.
yeah, and we get all your dates.
Okay. All right. Okay. So fortunately, this is an old laptop. So anyway, I think this is going to be easier. So I don't have to stand like there because I kind of really hate standing there. So classical robust control, the goal. Oh, no, this one's enough.
Oh,
No.
sorry. That was me.
Okay, now we have a bit of backdrop. Okay, I'll try and speed up a little bit. So the goal of classical robust control is typically to ensure that a control system remains stable, and that's important, and provides satisfactory performance in the presence of uncertainties. So we want to design controllers to be less sensitive to changes in the system or environment and able to adapt to unexpected disturbances. And there are two popular approaches in classical robust control. One is H-infinity control, which is essentially about minimizing the worst case performance of the system over a range of unstructured uncertainties. And then there's mu synthesis, which is similarly trying to optimize controllers to achieve a desired level of performance. Guaranteeing robust stability, again, emphasis on robustness, and I will explain later why I think this is a problem. But mu synthesis mainly looks at structured uncertainty. So I can have structure in the kind of uncertainty, which is, I think, important for quantum systems. Now, H-infinity control, I'm not sure about the applications now, because I realize most of you probably know nothing about classical robust control, and it's a different framework. It's just the mathematical modeling is a bit different. Let me just give you a very brief overview, like a 30-second overview. Most classical robust control is based on linear time invariant systems. So you have a formulation. So X is a state variable, it's typically a real vector, but you could represent anything. The U is a control and Y is the output, and A, B, C, D are just matrices that describe your plant, the interaction with the controller and the output. When you have an LTI system, a super convenient thing to do is to take the Laplace transform, because that turns this differential equation mess basically into an algebraic set of equations. And now you can define a transfer function that basically maps the control, which is in our case the input, to the observable, which is the output Y. And now on this slide, I think I make the vectors bold, and I put a little hat on to indicate the Laplace transform of the variables. I will drop that in a minute. So X is state vector, user control, Y the observables. And now we can make this is an open loop system, but we can actually easily extend this to model noisy closed loop systems. And here I've basically just written down the sort of extension. And again, here P1, this is now the plant. This is already in the Laplace transform formalism. And now you can see the plant would be our system. K is a controller here. Here you have a feedback loop. And so your input to the plant is your control, which can run through this feedback loop. And it has also external noise that you don't control, which would be your W. So that's kind of the model. And importantly, you have the control here can be conditioned on the state. So there's a state feedback. So that is important that we have state feedback. And now I used to think that this model was completely useless for quantum systems, but you will see in a minute that it isn't. Now, the important thing is we can extend this open loop transfer function to noisy closed loop systems. And again, we play the same kind of game. Because the Laplace transform, we can write the transfer function. In this case, we have a transfer function from the noise to the error variable, if you want. So that's basically, in a nutshell, the formalism that classical robust control typically uses. And the aims are set to minimize the worst case sensitivity of the system to unstructured uncertainties. That's for H-infinity control and disturbances. And again, usually a recurrent theme is that you want to ensure stability. The way you solve that usually is by formulating an optimization problem, and your goal is to find a controller, which in control, people like to call it K, for no reason whatsoever, that minimizes the H-infinity norm of the transfer function. And in this case, you can see the transfer function depends on the controller, the plant, which is with the system, and S is a Laplace variable. And the H-infinity norm basically is just the supremum of all frequencies of the largest singular value of this complex transfer function. Does that make sense? And typically you want to do that minimization subject to stability constraints. So virtually everything in classical control has kind of stability built in, and I'll explain in a minute why this is good and why it is bad for quantum systems. So the pros of this,
The German word for control starts with a K.
maybe that's, I don't know.
I'm just guessing, but it could be.
It could be a good point. So I don't know why it's usually in the textbooks, it's always called K. In my opinion, it should be B, because A, B, C, D, right? But anyway, so
I think I'm closer.
you're probably closer. So actually, this is a good point. So the pros of the H-infinity control approach, I need to make sure I don't get too sidetracked, because otherwise I'll still be talking at 5 o'clock and or you drag me out of the room like that. So the pros of this H-infinity control approach, it can actually handle a very wide range of unstructured uncertainties, unmodeled dynamics. You know, maybe you made some approximation in your plant and external disturbances. Some people would argue perhaps too wide a variety of uncertainties. The main cons is isn't easy to tune the cost functions to achieve simultaneous performance and stability requirements. Guess what? It's computationally sensitive near the optimal solution, exactly the same as what you would have, you know, for quantum control. But the biggest issue for us is that it's mainly a framework, a mathematical framework to formalize stability of linear systems. And now you're probably wondering, what has any of this got to do with quantum systems? And I used to think the same. I used to think, well, linear systems is not going to be very useful. But I will tell you in a minute that it's actually possible to put quite a few quantum control problems in this framework. But before I do so, I need to tell you a little bit more about the mu synthesis approach. Again, I don't want to go into too much detail. Again, for the mu synthesis, you start with a noisy feedback closed loop system. In this case, W is a disturbance, and you can see I've mostly dropped the bold and the half for the vectors and the Laplace transform. In this case, that is again the error, but now we have a structure perturbation. Again, we can write it down like this. And the important thing where mu synthesis is really kind of useful, it's similar to the H-infinity control, but one of the key concepts is a structured singular value. And a structured singular value, basically, we are just taking the minimum of the norm over all disturbances that basically satisfy a certain structure. And this determinant condition basically simultaneously guarantees stability, and it also guarantees, so this is the inverse of the singular value. And now what's interesting about this is that this gives you a bound on the performance degradation under bounded structured uncertainties. That is, if the structured uncertainties here, again, I dropped the infinities, this is the infinity, the H-infinity norm of delta is less of the disturbance, less than 1 over mu, then I can guarantee that the infinity norm of the transfer function will be less than mu, less or equal to mu. And I can also guarantee stability. And there's a whole lot of mathematical framework, and it's all based on complex analysis. So you might go, okay, how is it in any way useful for quantum systems? And it has limited applicability, but it has some applicability. So what's nice about this is that we can bound the performance. If the disturbance has a certain structure and a norm is bounded by this mu or 1 over mu, I have a bound on the transfer function. And you also get, in a way, it measures the system's worst case stability margin over a range of structured uncertainties and frequencies. So for mu synthesis design, the goal is then to design stabilizing controllers that minimize mu. And the pros of this approach compared to H-infinity control is it can handle linear and probably also non-LTI systems, although there are limitations on non-LTI systems. But we have tried to apply to some non-LTI systems. As said, you can deal with structured uncertainty, where the structure can be very complicated. could be parametric, could be unmodeled dynamics, it could be time delays, and it provides more detailed information about what controllers can achieve than H-infinity control. Again, the main cons from a control point of view, the design is computationally intensive. You may need specialized tools, and you need quite a bit of expertise to design these stabilizing controllers that minimize mu. So that sort of was my very brief introduction of to classical robust control. So how do we measure robust performance in general? Just a short list. So the H-infinity norm of the transfer function, that was basically what we used in H-infinity control, the structured singular value. And both of these are kind of similar in nature to gain and phase margins that determine how much a system's gain or phase can be increased before it becomes unstable. So that's a sort of more basic criterion. And then the H-infinity norm and structured singular values is sort of more sophisticated concept. So that's one set of performance measures, and all of these kind of rely in some way, implicit or explicit, on stability. Another set of performance measures that may be useful for quantum systems is sensitivity and the log sensitivity. And again, we can calculate that for structured perturbations, and we shall see that this does not require assuming any kind of stability, which may be a pro or maybe a con. And then there are also statistical techniques that are often based on Monte Carlo simulations. And we'll look at one little measure, which is based on the Wasserstein distance, which turns out to just reduce to the average fidelity under certain conditions, which is kind of neat. So we have these 5 different measures. Now, before I talk about quantum systems, I still want to explain a little bit why stability plays such an important role in classical control. It's a fundamental property of control systems, and is usually considered a desirable feature to ensure safe and predictable operation. If you talk to classical control theorists and you say, oh, my control system is unstable, they'll probably say, get out. Nobody wants an unstable system because instability can lead to unpredictable behavior, oscillations, and system failure. Just imagine an unstable aircraft. You may experience uncontrollable roll and yaw, pitch, oscillations, which leads to loss of control by the pilot and catastrophic consequences when the plane crashes. You probably wouldn't want to fly on an unstable airplane. I don't know about you. Maybe you're more adventurous, so you can see why you'd probably want your aircraft control engineer to have a good grasp of control theory and make sure they have designed the system to be stable. Similarly, another example, if you had an unstable chemical process, you could have a runaway reaction, which leads to an explosion and causes serious harm to people, the environment, and probably someone's bank account, right? So that's not good. So someone will have to clean up the mess, right? So that's clearly not good. So you can see why stable systems are desirable, and usually stability is baked into the mix. Now, before I move on, I thought I should maybe very briefly point out the stability criteria. Now, we don't have to actually go through all of them, because the only one I will be using later on is a pole zero condition. For an LTI system, it is stable if and only if all the poles of the transfer function lie in the left open half plane. Let's see, left, I think that's this side. So the left open half plane, that means a real part of all the poles should be negative. There's a couple of other criteria that are equivalent, but I think we can actually skip these because I'm not going to be using them. So why can't we apply this directly to quantum systems?
Sorry, aren't quantum systems always stable?
Marginally.
Linear.
I will get to this. Actually, they're always marginally stable, but I will explain in a second. So this is why I wanted to mention that pole zero condition and the difference between stability and marginal stability. So why can't we apply this directly to quantum systems? First, now you will probably, if you paid attention, you might say, oh, these LTI systems, terrible. Quantum control systems, the way we normally formulate them, are usually not linear time invariant systems. Usually they have a non-linear or bilinear input-output relationship. and the controls are time dependent. So that seems to be a problem. And I used to think that this was absolutely a killer, but it turns out this isn't actually a killer because you can often reformulate these as linear systems with state feedback, but the time invariance is still a problem. Another thing is a lot of classical control problems, they're frequency domain problems, and usually the transient dynamics is not important. You are interested in the long-term behavior, long-term stability. We're often not interested in the long-term behavior. The short-term transient dynamics is what you want if you want state transfer gate implementation and stuff. So we have time domain problems, and the worst case performance over a range of frequencies under decoherence, for instance, may not be that important. So the time domain issue is, I think, important, but probably a real killer is the marginal stability. When you talk about robustness, because closed systems subject to coherent control, they're always marginally stable because all the poles of the transfer function are on the imaginary axis. And that's precisely the boundary between stability on the left and instability on the right. So you have marginal stability, but you have no stability margin. Your stability margin is 0 if you're right on the imaginary axis. And
It can't get unstable, right?
it can't really get unstable, but it's kind of, marginal stability is almost as bad as unstable. It doesn't blow up quite as badly, but basically you have no stability margin. Now you could stabilize the system, but you can see, or you will see in a minute, that very often stability is actually undesirable. If you want to keep your systems coherent, you want the poles to be on the imaginary axis. You want to maintain marginal stability, because the larger your stability margin, the more you typically kill your quantum advantage. Another issue with applying this framework is we often deal with non-linear performance measures. So in control, people like the performance measure to be a linear function of the state. You know, ideally that's good, but many measures that we might be interested in, entanglement, concurrence, entropy, they're not linear measures. This, I think, is not the biggest challenge, but it also basically factors in making it more difficult. So what we would like for quantum systems is a theory for robust performance that does not rely on stabilization. That is, we can work with marginally stable systems, and ideally it should apply to a non-LTI system as well. I keep trying to press a button. Okay, so now how can we apply some of this to quantum systems, and where are the challenges? Quantum dynamics can be modeled in many different ways. Some people prefer the Schrödinger equation, others the Liouville equation, and I will not use either. I will simply use a real representation, which is based on the Bloch equation, and we can always do that. So the fact that quantum systems are complex is completely a red herring. It's completely irrelevant. We can always find a real representation, so it's really not an issue here. Did I say something wrong? From a robust control perspective, like we could actually make X the state vector complex and take the Laplace transform. It's going to be complex anyway, so it doesn't really matter. But we can always have a real representation, and I usually like that, where X is some vector in Rn. It's a quantum state. You could make it infinite dimensional, but again, I won't say anything about the infinite dimensional systems here. You can just choose a basis for the Hermitian matrices or any subgroup, subalgebra of the Hermitian matrices if you have constraints, and you can always expand your state and write it as a real vector. Then you can equally represent the system dynamics, the effect of the environment, and the controller by these real matrices. So that system dynamics would simply be a real representation of usually the Hamiltonian dynamics. This could be Lindblad dynamics. It doesn't necessarily have to be Lindblad. This formalism is pretty agnostic. What you shove in, but I think I will mostly be assuming that if you have environment dynamics, it can somehow be modeled in a Lindblad form, but the matrices can be anything. And then you have your controller. And again, if it's a coherent controller, basically, we write it like this, where these AM matrices are derived, they're antisymmetric, they're derived from Hamiltonians. And now when you look at this, you go, well, clearly most quantum systems, they're not linear time invariant. If this is your input, you plug this in, it's bilinear. And if the controls are time dependent, it's not time invariant. And I used to think this was a total killer. But it turns out it's actually not really a killer. It's just, you have to just reformulate it. Bilinear systems can easily be transformed to linear systems with full state feedback. Although the linear systems are generally not time invariant, but we can, for starters, we can start enforcing time invariance by simply assuming that we have time invariant controls. We can generalize that to non-time invariant controls, but then it's more difficult to prove anything. So if the controls were, so for instance, constant controls, then so which one is a pointer? That was clearly not the best idea I've ever had. Okay, never mind. It's fine. I will just point at the screen.
At the top, there should be a button.
Maybe. I see. There's a tiny pointer. I'm too blind to even see that. But if you have better eyesight than me, you can see a tiny red dot, I think. Excellent. So we can force a time invariance by just starting with time invariant controls. Then AC will be obviously time invariant, and then the rest of the system is time invariant.
Can I ask a question? Since we're talking about control, how do I control that, for instance, this stays in a state space, or, right? I mean, the solutions probably should stay in a state space in some situations, or observables of a certain form, unitaries. Is that already implemented with a control function that you can make sure they stay in this, in some kind of subsets of Rn?
If you wanted to, you could, for instance, if you had a subalgebra, like for instance, if you have if the dynamics is on a subgroup, you could choose a subalgebra, and you could actually force your state basically to have symmetries already built in. Now, if you want more complicated things, you would have to impose constraints.
I mean, you often, I mean, subalgebra is fine. I love that, but you want to stay in the unit sphere of that. Right.
In this case, you can totally build this in, because if you expand in the right way and impose a trace constraint, I don't want to go into all the details, but
It's important
yeah.
to have that thing.
Absolutely, these constraints are important, and some of the papers we wrote were basic. You just had to build a stupid constraints in, but I don't want to bore you too much with those details, because I think you know I want to give more of an overview and then present some results. So let's see, where were we? We have bilinear systems, we have non-time invariant controls, but we're just going to service time invariant controls anyway. Now, in this case, we can actually easily reformulate a bilinear system as an LTI system. So basically, x dot is ax plus bu, y is, I dropped the d because usually in quantum systems, we just assume the d is 0, but you could put it there. So y, the output depends on the state, and C would just be a matrix, for instance, that determines the infidelity of your gate or the state infidelity. So that would be a linear measure of.
Sorry, I don't understand. What is BU? U is the control?
U is a control, yes, but I will basically, what I'm going to do is now U is a control, but now the control will be a state feedback. So I define the control to be the constant controllers and then the state of the system. And now before you drag me out, this is a state feedback. It induces there is a feedback loop there, but it doesn't require any measurements. It's kind of like an op-amp where you take the output voltage and connect it to the input via resistor. You don't have to measure the voltage. The op-amp doesn't have to measure the voltage. I don't want to get into a philosophical discussion whether the system knows the Schrödinger equation or not, but this is a state feedback, but it doesn't require any measurement. We don't have to measure the state. It's just there. If I define U as a state feedback like this, then you can see I can take that bilinear system, or you could even have, you can make it more nonlinear by defining this feedback in the right way. I can actually turn it into an LTI system. I can then happily take the Laplace transform and define a transfer function. So, and now you can see why I talked about transfer functions and why I talked about the stability criteria. So remember we said the system is stable if the pole of the transfer functions are in the open left half plane. Look at this transfer function. The poles of the transfer function are the eigenvalues of this big block matrix A. For Hamiltonian system with coherent control, A and AC are antisymmetric. Those eigenvalues are purely imaginary, so they are in a marginal stability regime. If we add an environment to this, typically, because the environment will, well, if it's a proper environment, it will not be antisymmetric. It will be anything. It could be a Lindblad term or something else, but it will not be antisymmetric. And in general, if you add the environment, then you move the poles from the imaginary axis to the left. I guess that would be this way. That makes sense. And that, in that sense, the environment typically acts as a stabilizing controller, and you can actually make this mathematically rigorous. But right now, I'm just not going to bother. You kind of get the idea. And now you can see why stability margins are not necessarily a good thing. But hopefully on the next slide, I'll elaborate on this a little bit. So the curse, what I call the curse of stability, if there's no environment or the interaction with the environment is negligible, A is 0, the eigenvalues are, as I said, on the imaginary axis, and that's a marginally stable case. When you have an open system, the eigenvalues typically have negative real parts. Now I should say, maybe not all of the eigenvalues. There's always going to be 1, 0 eigenvalue because there's at least one trace constraint. And if you have pure dephasing, there are multiple trace constraints, and you have to then still massage it a bit to get rid of the trace constraints. But just to keep things simple, like the closed system marginally stable, the open system is stable, and the larger your stability margin, typically, the more you're in the classical regime, and you lose the quantum advantage. Not always, but very often. So when I looked at this, it was like, so the environment acts as a stabilizing controller. The stabilized states in dynamics are mostly classical, and the stability margin, the larger my stability margin, which is what I classically want to maximize, the worse my quantum performance gets, because in I think on Monday or Tuesday there were several talks on rates of entanglement loss, and they think these are actually directly related to these stability margins. So when you look at this, you go, robust quantum control is probably hopeless, but turns out it's not as hopeless. I think it's a challenge because you want to maintain maximum quantum advantage. You don't want large stability margins in most cases.
Exactly by quantum advantage.
Basically, I just want the dynamics to be not classical. For instance, if your environment stabilizes a classical state, the system can have very robust performance, but very often your dynamics more or less, in the long run, it will behave classically, or you stabilize a classical steady state. Say, simplest case would be you have your lovely entangled quantum state, and then you have dephasing that kind of acts as a stabilizing controller and turns it all into a classical ensemble, and that's stable. There are different notions of stability. At least Lyapunov stable, and from a robust performance point of view, you would say, yeah, I have a stabilizing controller. It's just not a very good one. It just doesn't do anything interesting, right? So that's where I see it's a challenge. So that raises the question, is robust performance without stability possible, especially given what I said in the beginning? When you talk to classical control theory people, they'll say, you don't want unstable systems, bad things happen. But bad things happen when we have stability, right? Because we lose most of our quantum advantage. So then that, of course, leads to immediately to the next question. What actually would qualify as robust performance of a quantum system? You know, what do you mean by robustness when you have marginal stability? You don't want classical robustness. We must consider the marginal stability, and also we would like to extend this to non-LTI systems, although by clever definition of state feedback, you can actually transform a lot of bilinear and even non-linear system in terms of, you can formulate them in terms of linear systems with state feedback, which does not require measurement. It's kind of like closing the loop in an op amp. It took me a while to convince myself that this was the case. And if the system obeys the Schrödinger equation, it doesn't matter. When we first published this paper a few years ago, we had a philosophical discussion with the reviewer. We said, no, you can't do that. But I think it's totally okay. The system does not need to know its state. It just needs to obey the laws of physics. So what qualifies as robust performance, and how can we measure robust performance? Any measures that require stability will be of limited utility. I don't want to say that they are completely useless. There are exceptions, and I'll show you an example, but they're probably not that useful. And of course, quantification of robust performance would involve assessing the system's ability to cope with a wide range of uncertainty and disturbances. And very often you try to make it robust with one aspect, you fall off a cliff on the other side or so. Maybe not quite. So it's challenging. And then, of course, we need performance metrics, which may need to include nonlinear measures such as entanglement measures, concurrence, and stuff. This is probably not the biggest challenge, but the nonlinear performance metrics also makes the analysis somewhat more challenging. Now, I want to give you one example where we have managed to apply mu analysis, and maybe we can structure singular value analysis. And where I think it can be useful in general is probably reservoir engineering, especially reservoir engineering problems where you design, say, a Hamiltonian and an environment, and very often these are actually not dynamic systems. So maybe the parameters of the system could be time invariant by design. And so you have in this case, you have a class of quantum control problems that you can easily formulate as LTI systems, and because you're trying to stabilize the system, typically, in this case, you meet the stability criteria. And one example, this is from an old paper, would be two qubits either in a lossy cavity with no interaction, but the qubits interact with the cavity, or you could put the qubits in separate cavities that are coupled. There are lots of different variations on the theme. And then by designing the interaction with the cavity, here you can see you just have your Hamiltonian part, and then you have your Lindblad terms, which has collective terms. There's usually a collective damping term, a cavity loss, and then you have the interaction of the system with the cavity. You typically adiabatically eliminate the cavity. You play a whole lot of games. So that system that was published a few years ago. And what we did in a more recent paper, we actually analyzed the robustness of this system as an example with regard to different structured perturbations. And the structured perturbations we looked at was the effective qubit cavity coupling. We looked at detuning of individual qubits in the cavity, collective decay, and single qubit decay. Again, as an unlimited variety of structured perturbations that you could study. These just seem like fairly obvious things that you could do. So we defined these structured perturbations. And again, I'm not going to go through the entire formalism and all of that. I just want to show you some pictures of what we could potentially get out of it, what we can learn from this, and obviously where the limitations are. So I think the first two pictures, we show the error gain, which is just the H-infinity norm of the transfer function as a function of frequency. For a small perturbation strength delta. So I should say S is the structure in a lot of talks yesterday and today. I think that would be the V, and the strength of the perturbation in control is typically called delta, which most people call epsilon. So think of structure, basically SK is a structure and delta is a strength. So on the left, we basically see the norm of this transfer function as a function of frequency for small perturbation, and delta is one that's a much larger perturbation. And what we could get, for instance, is the norm of the transfer function. We can compare different structured perturbations, and you can see here, you can see that for small perturbation strengths, the most sensitive part is actually the zero frequency part. that's where it peaks, and you can also see some perturbations are worse than others in terms of when you look at the norm of this would be the error gain. As you go to larger perturbations, the picture changes, and you can actually see that S1, the most sensitive frequency range, is no longer 0. So kind of it gives you some kind of frequency resolve picture. So you could look at different type of structured perturbations, and then you could basically look at which frequencies are most sensitive, and perhaps if you can experimentally characterize your frequency spectrum, you could say more about.
So can I ask a question? I agree with your trick to rebrand the bilinear control as a linear control. That's kind of cute. But what is the operational meaning of this norm of the transfer function in this context? Usually you would care about, let's say, the fidelity of preparing a particular state. So if this norm is really big, does that have an impact on the fidelity, and how is the relationship? Does it have a meaning?
Yes, in this case, basically, for this particular problem, if the norm is big, that means you just have a large error gain. In this case, it's still stable, so it's always going to be stable, and
You always go to the state that you want. Or you go to different states.
you could go to a different state, basically. So it basically will just tell you. So this is basically the transmission of the disturbance to the error. So the larger the norm of the transfer function, basically the larger it quantifies the error. But in this case, it's always stable.
So how does it quantify the error? Sorry, that's the part I didn't get. The transmission of the disturbance to the error, I don't understand what that means. So I mean, how does the fidelity depend on this
Okay, let me see.
thing?
Well, the fidelity depends on, well, where did I have the? There you go. I think I had it up there. So here, did I only put? Okay. So here I've only got this version. Then I thought I had the version that had the error as well. Maybe I only did this in a classical framework.
Okay, I mean, if you don't have it,
No,
I can check the paper, I guess. But
you could probably get more information from the paper. And it's again the precise interpretation. Where do I have it? Here. Here, this would be your output, and it basically would quantify how much the best way to the transfer function is a complex function. So basically, it kind of quantifies the gain of the error. Like if you have a disturbance, how large the error is. So the larger the transfer function, the more sensitive the system is. And you can directly relate it to the fidelity, because basically that comes in here. So it's C, so you have the state, and then your C matrix basically quantifies the infidelity. So I think we have a bit more in the paper. And I know it's very difficult to explain without really going into a lot more detail. And I said, this has a lot of limitations, but you can, I think, maybe get some useful information. Let me see. So now I think I would probably really need to explain more of this. Where was I? I think we're nearly there. So what's interesting, basically, we can look at the error gain, and what we usually want, we want the error gain to be small, and so you could compare at least the error gain as a function of frequency. You can then take the maximum frequency and see the maximum gain. And here, for instance, you can see as a strength as a function. So we take the maximum of all frequencies for all delta and stuff, and then you can see that S3. The maximum gain is much larger than for perturbations S1, and for S1 you have initially a steeper increase, basically, but you peak at a lower value, while for S3 this increase not quite as steep, peaks at a higher value. Yes, so again, you could analyze these things. Does it give you like all of the answers? It doesn't. You can also look at the frequency where you achieve the maximum gain, and so which frequencies perhaps are the most critical frequencies. That's what you could get from this analysis.
So what is the output? What do I need to think of for y? What is y?
Why? In this case, said this is basically the error variable which quantifies the infidelity here. I think I think I have the next slide where we also looked at. So here's actually a plot, the log sensitivity, which I'm going to introduce in a minute, the concurrence and the maximum eigenvalues. And so here you can see. Did we not plot? So here we only plotted the concurrence, but the error variable would be the infidelity here because we wanted the linear performance measure. But you can also here, this was one plot we did for the detuning. So again, I think this analysis, this mu analysis on its own doesn't give you a full picture, but it does maybe give you something useful. You can look at different structured perturbation. You can basically, so if you want the infidelity, you just choose basically your matrix C, which maps the state to the error. You can look at different error variables. You can look at the frequency response, and you can relate it to the concurrence as well. But this we did sort of in a semi like manual way, and this was just for the strength of the detuning. And I think here the point of this plot was that if you look at the concurrence and the maximum eigenvalue, they're kind of concordant. Okay, so I really need to like speed up. Then we've actually applied this also to extend this to transfer functions for the error dynamics. And again, I'm not going to have time to explain this, but this could be useful. For instance, if you had a model and an approximation, you could actually try to quantify how much the dynamics diverges based on like your two different models. I think I'm not going to have time to explain this because I want to say something about the log sensitivity, because that's probably the most immediate thing that you could apply for quantum systems. It's basically a dimensionless differential sensitivity measure that quantifies the effective parameter uncertainty to disturbances or disturbances on a performance metric. Again, we start with the our LTI system formulation. Now here you have a structured perturbation, and we have again a magnitude and a nominal value. And now the performance metric is a function of the state. And again, I should really explain that more carefully, but basically the log sensitivity, it's just you have your output. This could be the fidelity error. In this case, we called it Y. It could be Z. You differentiate this with respect to the parameter delta. You divide by Y over delta, which then becomes delta over Y. So this is why it's called the logarithmic sensitivity. It's closely related to this differential sensitivity. The reason control theory people like the logarithmic sensitivity, because it's dimensionless by design. But there are some issues with applying it, but I'm not going to have time to go into the details. The advantage is that this is very much analytically tractable when the performance measure is linear, at least. It can be applied to time domain control problems. It doesn't have to be frequency domain. We can easily extend it to okay, I should probably not say easily, but it probably can be extended to nonlinear performance measure and even non-LTI systems. That's not completely trivial, but for instance, we have managed to extend this to piecewise like gate synthesis with piecewise constant controls. The limitations of the log sensitivity is that it's a local sensitivity measure, and so we don't get bounds on the maximum allowable perturbation that ensures certain performance, as we had with the mu, right? When the disturbance, the infinity norm of the disturbance was less than a certain value, you could say that the error in your output variable was bounded. So we don't get these bounds, so that's still a challenge. And currently the utility is mainly limited to analyzing controllers, but we could probably actually build this log sensitivity condition in. And let's see, let me just show you some results. So we've actually done some analysis on this. And we started with this a few years ago. And initially we just did this completely numerically. And the numerical results were very, very interesting because they seem to suggest that there wasn't really a trade-off between fidelity and sensitivity, which you would classically expect. But when we analyze this rigorously, we can see that the log sensitivity, here this is a 2-qubit in a cavity problem. As time goes to infinity, the log sensitivity diverges polynomially, typically linearly. And here we analyze the case of state transfer in spin chains with engineered chains, and you can see that you get divergence at whenever you get perfect state transfer. I think here, this is a logarithm of the error is in red. So when the error goes to basically 0, you see the divergence. So there isn't any violation in what we expect. So there is a trade-off between sensitivity and performance. But actually, so the last thing I'll show you, it's not a fundamental limitation. And basically, you have a whole lot of preprint references where we analyze a whole lot of data sets. And even though I said we can show that in the limit where the error goes to 0, the log sensitivity still diverges. In many cases, we can actually look at large sets of controllers, and there's a lot of variation in the log sensitivity. So that potentially means we could jointly optimize for log sensitivity and fidelity. And I think this isn't even so these are the preprints. Some of it, I think some of the papers have already been published, and they should all be published. It probably Transactions on Automatic Control or one of these journals. And I think I'll just skip the statistical robustness measure and go to the summary. So I promise I'll be quick. So again, robust system and control design is a prerequisite for technology. Classical robust control does offer some interesting tools, but they're insufficient. Age infinity and mu analysis may be applicable for reservoir engineering. I think this is where some open system control. I think the differential log sensitivity measures are useful, and statistical robustness measures, which I haven't had time to talk about, may also be useful. But as I with the statistical measures, it's a bit of a problem. But again, we've also done some work to see if there's correlation, if we can correlate the statistical measure to the log sensitivity. But what we really need is a framework for robust control and system design, taking into account lack of time invariance, marginal stability, nonlinear performance measure. And the last thing I wanted to say, so I've been roped in basically to be like an editor of one of these new journals. And this journal, I just wanted to say, if you're interested, this journal is supposed to be different from how most journals operate. Cambridge University Press. The idea is you submit a question. So for instance, if you had a workshop or something like this could be really interesting. You define a question, and then people can submit various pieces of work. It could be working papers, it could be data sets, it could be code, it could be papers, it could be analysis, a piece of methodology. And when you got enough responses to the question, we close the question, and then hopefully somebody else submits a new question. So I think these are the questions we have currently submitted. And, they'll be open for a while if you wanted to contribute. And of course, then people can define other questions. So again, and I think it's open access and also open peer review. Whether that's a good idea, I don't know. But the idea was basically people can submit different pieces of content. It's question based, and it'll be open peer review. So it's completely, I don't know, we'll see. This is completely new, and I just want to, if you're interested, I can tell you more about it, and I promise to shut up now.
Thank you very much.